So we just saw what one hot coding is. It is just converting one of these classes into an m digit binary number or an m element binary vector um, that encapsulates what the output is. Okay, the class 3 is represented by five numbers if you have five classes, where the third element or the third digit is a 1 and the rest are 0, etc. Um, Now, why are we converting these nice integers into these much longer binary vectors or binary numbers? It's because this way of representing the class has actually the interpretation of probability. So if you say the first digit is P1, the next digit is P2, etc., and the ith digit is Pi, then a number like this basically says that the probability P3 that it belongs to class 3 is 1, and the probability that it belongs to class 1 is 0, class 2 is 0, class 4 is 0, class 5 is 0. In other words, that's what this number represents, or this vector represents. If this is P1, it says that the probability that a particular data point belongs to class 1 is 1, and given that that's the case, the probability that it belongs to class 2 or 3 or 4 or 5 is 0. Okay, so this way of representing this essentially has this nice probabilistic interpretation. Okay, now that we've defined what this thing one hot coding is or dummy coding is, um, we are now ready to write down an expression for the multinomial logistic loss function or the cross entropy loss function. Um, so let me just state what it is. Um, just like before, we computed for each data point and then sum over all data points or take the mean over all data points. So what do we want to do? We want essentially um, the probability expressed by this expression, right? So underlying all this, we have this expression for the probability that something belongs to class I or something belongs to class J or whatever. This is the expression for the probability. This is a prediction by the model of what the probability is that a particular image, say, belongs to a particular class. Okay, what do we want to do? We want to make sure that that probability predicted by the model is actually as close to this one hard-coded class, right? So if it says the probability that a particular image belongs to class 3 is 90% and everything else is small, ideally the actual data should be that it belongs to class 3, right? So these estimated or model predicted probabilities are Qi, and um, the actual probabilities are basically the actual class or pi given by pi, and we want to make sure that those things are as close as possible. So the loss function basically is kind of a difference between the two things, and we want to minimize that difference, right? It's not exactly a difference as we've discussed before. Instead, it's this weird or superficially weird thing where it's sum over pi log qi. For each data point j, we have this expression over all the different classes. This is sum over all the classes. Um, so this is exactly analogous to the logistic loss function that we had. And then we can sum over all the data points or take the mean over all the data points. Okay. So this is basically the cross entropy loss function or the multinomial logistic loss function. Um, this expression also works if the data itself is in terms of probabilities and as opposed to ones and zeros like this. it works out when that's the case as well. Although usually the data is of the form that, okay, this belongs to class A, this belongs to class B, rather than this is 90% sort of belongs to class A and 10% belongs to class B. You generally don't see data that looks like that. Uh, but maybe there are some situations where you get data like that. And this procedure will work for that as well. Now, what are the unknowns? Now we are essentially trying to minimize this quantity L. The unknowns are all the B's, the B vectors that sort of correspond to each class. So we want to solve for all these B vectors. Now we have M different B vectors, one for each class. We still use some numerical procedure like fmin-nunc to solve the optimization problem. Now it's one big optimization problem instead of M smaller optimization calculations, right? So it's just like you're solving for everything all at once. Once you solve for B, we can then use the formula 1. So just recall what the formula is. This formula, which gives you the predicted probabilities. So once we solve for all the BIs, you can use that formula 1 to actually predict the probability that a given data point, for instance, an image, belongs to a particular class. And because that formula will give you a probability for each class, like given an image, will give you the probability that it belongs to class 1, class 2, class 3, etc. And all the probabilities will actually sum to 1. This actually gives you a very natural, nice way of saying what's our first best guess, second best guess. Not only that, we can assign our confidence level in what the first guess, second guess, which is basically the probability. We can say with 60% probability, it's going to be this number or this class. And with 30% probability, it's going to be this class. And then with 10% probability, it's some other class. So I think this is really cool because expressing a confidence level is actually a nice feature, and it's always nice that when you can do that, as opposed to just making some kind of a prediction. Okay, so how big is an optimization problem is this? If you recall, like let's say we are using this linear separating boundary, and let's say your data point is in 784 dimensional space as an MNIST. It could be something else. Then each BI vector has 785 elements. Then in approach number 1, which was doing M different optimization problems, you have 785 unknowns, and then we are doing 10 or 20 or how many other optimization problems with those unknowns. In approach number 2, we are doing one big optimization problem with M times 785 unknowns. In other words, if M was 10 and you had 785 unknowns per class, then you would have 7,850 unknowns. So this is a bigger optimization problem, but just one of it. This is a smaller optimization problem, but you solve M of them. Sometimes this might be faster, sometimes this might be faster, but overall, the results from this would be considered better, more holistic. Okay, and that's because, like we said, it gives meaningful probabilities for each class and somehow treats all the classes all at once rather than making this independent assumption. Then I have sort of a quick technical aside. You can read through this to give some motivation as to why we are using this logistic log loss function. Where does the log come from, and so on. So you can read through that, and if you have any questions, we can talk about it.